We've done it. We're finally here. Our last new lesson for Topic 2 in AP Calculus BC of series convergence tests. Our final concluding lesson is actually a very quick one, and it's on the difference between absolute and conditional convergence. This is a nice way to really tie everything together we've done, but honestly it most closely ties to day 30, that alternating series test that we learned. So let's see what we can do with this, and it should be, I think, fairly quick. I have given you on the opener the alternating harmonic series, but presented in two different ways. This is probably more traditional, though I did leave off the 1. So it's 1/2 minus 1/3 plus 1/4. But if you leave off one term, it doesn't really matter. And then over here, look what I've done. I'll try to highlight the terms. We have 1/2, and there's a 1/2 here. And then there's the 1/3, so nothing new there, right? That's right there. But then I took the minus 1/5 and I wrote it before the positive 1/4, and I really should do better with colors on this. I'm going to try to have the greens represent the negatives here. I wrote the negative 1/5 before the positive 1/4, but I'm allowed to do that. I mean, you can switch terms around. I mean, that's like saying that 2 plus 1 is different than 1 plus 2. It's not, right? We're allowed to change the order of our numbers here. And then I took the positive 1/4 and I wrote that one next. There's nothing wrong with that. That looks pretty good. But then what did I do next? Well, instead of doing plus 1/6, I think I did a minus 1/7 and then a minus 1/9. All right, and then we, of course, add on the 1/6. And so really what we're doing is we're taking one positive number and then two negatives, and then one positive number and then two negatives, and so on and so forth. Now, thinking about this, and if you wanted to put this into words or maybe numbers, you might want to use a calculator on it, but we can just do basic bits here. 0.5 minus 0.33 repeating is going to be something that's positive, right? 0.167, something like that. And then if we add on 1/4, that's definitely going to stay positive, right? 0.3 and 0.417. And then if we subtract off 0.5, then we're still going to stay positive. So I'm pretty convinced at least that this sum is greater than 0. However, if we work with our second one, we start at 0.5 and then we subtract off 0.3. I don't know why I put an extra decimal. And then we also subtract off 0.2. So at this point, I think these will cancel, and that's going to leave us with really 0.033 repeating, something negative. And then we're going to get 0.25 more, so that's going to add on. But then we're going to get two more negatives here. And then we're going to get a little more positive, but then we're going to get more negative. And so it actually turns out that this sum becomes negative, while the first sum becomes positive. And that is really weird. Right? That is the same series, just written in a different order. And, of course, manipulating this order and putting two negatives in a row. We could have made it really negative. We could have done one positive and then four negatives in a row, and then one positive, then four negatives. That would have been even a different answer. And so it turns out that we can actually rearrange this convergent series to get different sums, which I think is fascinating. So we're going to actually use this in a part of our definition. If you can find more than one sum from a series by rearranging it, then that sum is called conditionally convergent. So the fact that we can make more than one sum out of this alternating harmonic series means although the alternating harmonic series is convergent, right, we're making sums, it converges to a sum, it is conditionally convergent because depending on the order changes the actual sum. And in fact, it's been proven that you can rearrange a conditionally convergent series to make any sum you would like. So if you wanted to make it sum up to -7, it's possible. Just put a bunch of negatives first and continue that pattern, you'll be fine. You wanted to make positive 1 million, it is possible. Do tons and tons of positives and then one negative and tons of positives. You can get there. However, if the series always equals the same sum, regardless of how you arrange it, then that series is called absolutely convergent. And I don't want you to think, oh, it's because of the negatives. Any alternating series, I bet you can rearrange that to make any sum. Actually, you can't. This is the wild part. If this is the sum of 1 over n, I'm sorry, negative 1 to the n over n, I've got to tell you that negative 1 to the n over n squared, which is very similar to this, right? If we follow the same pattern, this looks like they used 2 first. So that would give me 1/4 minus, and then we use, of course, 3. So minus 1/9 plus 1/16 minus 1/25, and so on and so forth. If we do that, no matter how we rearrange it, shockingly, we always get the same sum. Again, mind-boggling. Now, we probably need a faster way to do this. So instead of just saying, oh, absolute versus conditional is where you rearrange it to find different sums, well, we can't actually sum this up by hand. That would be really obnoxious. So how do we know if it's absolute versus conditional? So luckily, we have a faster way to do this than just rearranging the series. And that actually comes down to absolute value, which is pretty funny because I just said that it didn't matter that there are negatives versus positives here. Well, it does kind of matter. So let's take a peek. If you're given some series where the sequence a sub n is here, and of course we're summing this up. If this is an infinite series, then this series is absolutely convergent if you apply absolute value to it, and the absolute value of that series is still convergent. The absolute value really does strip away the alternating part, and so if the series is still convergent after the alternating part, then it is absolutely convergent. And of course, the opposite of true. A series is conditionally convergent if after you take the absolute value, the resulting series is divergent, right? And a really easy example is going to be this one down here. We're going to look at the alternating harmonic series. Okay, so our goal for this is to determine if these series are absolutely convergent, conditionally convergent, or divergent. And actually, I'm really going to work backwards. So we're going to start with divergent here. Is this divergent? Well, no, this is certainly not divergent for any number of reasons. First, we know that 1 over n decreases. And we also know that when you have an alternating factor on a decreasing series, that series is convergent. That's the alternating series test. The second reason is that this is the alternating harmonic series. And if you state this is the alternating harmonic series, therefore it's convergent, you're fine. But what type of convergent? Is this absolutely convergent or conditionally convergent? Well, the way we check that is we say we're going to go ahead and find the sum from 1 to infinity of the absolute value of negative 1 to the n over n. Now, all the absolute value is going to do to most of these series, because really most of the series, if not all the series we check for absolute versus conditional convergence will be alternating series, is it's just going to take away the factor that makes it alternate. So it's going to become just positive 1, because the absolute value of this guy down here is just positive 1 over n. It doesn't affect the n at all, because n is always positive. And so once we do that, we can hopefully see that this series is the harmonic series, which diverges. So we'd say something like as n equals 1 to infinity, the absolute value of negative 1 to the n is the harmonic series which diverges, right? Good so far. But the sum from n equals 1 to infinity of negative 1 to the n over n is the alternating harmonic series which converges, then the original series, which I've already written once, but I'm doing it again, negative 1 to the n over n is conditionally convergent. And that is because when we took the absolute value, it absolutely did not converge. Conditionally convergent is the idea that this series only converges on the condition that it is an alternating series. If it doesn't have that condition, then it no longer converges. So 1 over n only converges with the condition of having an alternating factor. Now, let's take a look at its counterpart over here, and I'm not going to go as in-depth in this one. We're going to look at this we see the alternating factor. We know it's an alternating series, 1 over n squared, decreasing. This converges. It's the alternating harmonic, or it's an alternating series test. So we're just going to go ahead and test the absolute value of this series and see if it converges. And of course, the absolute value is just going to take away that negative n to the n plus 2, and it leaves us with this. What can we say about this? Well, this is a p-series, right? This is a p-series with p greater than 1. P is 2 in this case. So we know that this guy is convergent, right? Over here, this one wasn't convergent. The absolute value is convergent. So we would basically say as this is convergent, then this is absolutely convergent. Though we'd probably say it in nicer sentences than just drawing random arrows. But I think you get the idea. Really, that's all there is to absolute versus conditional convergence. Nothing too complicated after that. We're going to finish off today, though, with 2 more questions. The first is a multiple choice, and the second is a free response. It seemed fitting with our last day of this, and then after that you have a little independent practice, and the next few days are just review before your second test. So here we go. Which of the series are conditionally convergent? Well, we're really just comparing it to the absolute value of each of these. And I'll go a step further and say this is n to the 1/2. These are all p-series. We know that this diverges, converges, diverges. So conditionally convergent, these two both converge because they're alternating series that decrease, but they only converge because of the condition of negative 1 to the n. Therefore, 1 and 3 are the only conditionally convergent sequences, right? This one over here is absolutely convergent. All right, here we go. Now, I will tell you in advance that this is a pretty darn tricky free response, especially part A. Part A asks us to evaluate the improper integral, and I think people will probably struggle on this one. I mean, hopefully you've been keeping up with your derivative rules because you really need it here, but if you haven't, you're going to struggle, and that's okay. We're still so far from the AP exam. We will get our practice in. B and C, though, have some great series questions, and I really like concluding with this one. So honestly, I would say go ahead and pause, and it actually helps to do A before B, before C. Remember, most free responses don't have that where you need A to do B. You generally don't need that. But I would say that problems that have series and sequences actually do tend to relate to each other. And so what I would suggest you do is try A first. And then if you get stuck, or if you get the right answer, watch the video, skim through, make sure you got it right. Then try B, and then watch, and so on and so forth. So kind of take it in pieces. All right, pause me, ready, set, go. Okay, you're back. Hopefully you're doing okay. Let's go ahead and take a look at this. We needed to find the the improper integral here. So we're going to tackle a couple things. I'm actually going to keep the infinity up here for a while because there's a few other things I need to manipulate with this integral. In particular, I just don't want to write the limit over and over again. I don't know how to take the antiderivative of that. I think U substitution isn't going to help too much yet. However, we might recognize that we're used to seeing a 1 over x squared plus 1. And that should spark some sort of distant light bulb of saying, oh wait, that's an inverse trig function. That's inverse tangent if we take the antiderivative. So I'm going to do my best to make this look like a plus 1. And to do that, I'm going to divide everything by 9. 9 divided by 9 is 1. Okay, as long as we divide top and bottom of a fraction, we're allowed to do that. And then cleaning this up even a little bit more, I'm going to factor out the 1/9 that was on top. And then instead of x squared over 9, I want this whole thing to be squared. So we're going to say x divided by 3 squared. And now we're really fitting that form of a 1 over something squared plus 1. I think maybe one more step here. I should probably get that limit guy rocking and rolling, right? The limit as b approaches infinity for our improper integral, 3 to b, 1 over x divided by 3 squared plus 1. And now I think is the time for our u substitution. So we are going to let u equal to x divided by 3, or 1/3 x if you prefer that. It's starting to look like an A. Let's make that a u. And I think that tells us then that du is just going to be 1/3 dx And I decided to apparently stop writing dx, which was quite rude of me. There we go. And I'm looking at this saying, I don't see a 1/3 dx, so maybe we can multiply both sides by 3 and say that 3 du is dx. Of course, this is I wanted to say improper again. This is a definite integral that has limits of integration. So if we change the u, we should also probably change my limits of integration. So I want to change my 3 over here. So we're going to find u of 3. And that's defined back over here. So this becomes 3 divided by 3, which is 1. So my lower limit is 1. And then my upper limit, u of b, well, we're just replacing x with b, and that becomes b divided by 3. Cool. Now we can actually do some antiderivative stuff. So let's rock and roll. We have 1/9 times the limit as b approaches infinity of the integral from, now it's 1 to b over 3, times 1 divided by u squared plus 1. And instead of dx, right, dx is getting replaced with 3 du, so 3 du. Now I'm going to clean this up just slightly. I'm going to bring the 3 out front. And actually, because I don't want to run out of space, I'm just going to take the 3. If you move it out front and combine it with the 1/9, it becomes 1/3. Ha! Go erasing a computer. All right, antiderivative time. 1/3 limit as b approaches infinity. Antiderivative of that is just the inverse tangent of u from 1 to b over 3. We should substitute everything in because we changed the limits. We are going to have an easier time. We don't have to change things back. So it becomes becomes the inverse tangent of b divided by 3 minus the inverse tangent of 1. Now, you might struggle a little bit on this, and that's okay. No judgment here. We don't do a lot with inverse tangent. We did one other inverse tangent problem, and I reminded you of one thing. I said, I know that tangent is sine over cosine, and I know that that becomes undefined when cosine is 0. Where is cosine 0? That's when x is pi over 2, or 3 pi over 2, or even negative pi over 2. So that means my asymptotes happen at pi over 2, 3 pi over 2, or negative pi over 2, negative 3 pi over 2, so on and so forth. And so I'm going to put in the asymptotes of regular tangent, right? This is all regular tangent, and then hopefully you remember the shape of regular tangent. It looks like this. So this is the graph of tangent of x. Technically it repeats, so it does that over and over again, but for the inverse we won't need that. Okay, well now let's actually go ahead and look at the graph of inverse tangent. Right? Inverse tangent is going to take those vertical asymptotes and turn them into horizontal asymptotes. So we have this guy at pi over 2, we have this guy at negative pi over 2, and we need to remember that it's going to look very, very similar, except now it's going to approach the horizontal asymptotes instead of the verticals. So when we work this guy right over here, when we're adding an infinity, or bringing b to infinity, the inverse tangent of something infinitely large, inverse tangent is approaching pi over 2 minus, and then we have the inverse tangent of 1. Going back to sine divided by cosine, we have to think to ourselves, okay, sine divided by cosine equal to 1. Well, to get a fraction equal to 1, the numerator and denominator need to be the same value. Where are sine and cosine the same value? They are the same value at pi over 4. And there we go. Now, you could go through and you could clean this up. In fact, I think if you try it, you'll find you end up getting pi over 12, which is nothing too bad. But again, this is probably as far as you need to go. You unfortunately cannot stop here because of that limit. So they were pretty tricky. They needed to make sure that you could evaluate that because you can't plug a limit into a regular scientific calculator. So just be careful. Does inverse tangent come up often? Oh gosh, no. This is the hardest inverse tangent problem I've ever once seen on the AP exam. Should you know it? Sure. So maybe go back and review those inverse tangent stuffs. All right, moving on to B and C. Much quicker this time, I promise. Looking at B, they want us to decide if this series, and actually I'm going to rewrite this series, so we're going from n equals 3 to infinity. F of n means replace all of this with n, 1 over n squared plus 9. Does that converge or diverge? And state a test. Well, honestly, at first thought, I was like, well, wait, if we just take off the 9, then we can do the direct comparison test. That'd be pretty easy. We could even do the limit comparison test, and I think that'd be pretty easy too. But there's a faster way, right? They made you do all this work up here, and there is a reason for their madness. Because we should notice that f of x up here, f of x equal to 1 over x squared plus 9 is three things. It is continuous, decreasing, and positive. And when you have a function that's continuous, decreasing, and positive, and you are able to take the integral of that infinite series, then what does that tell you? Well, if we found an answer here, then that means that our original series is convergent by the integral test. So f of x equals 1 over blah, 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 and then we say something like, as the integral from 3 to infinity of f of x dx equals pi over 12, then the integral test proves the sum from n equals 3 to infinity of f of n converges. And bam, that is a very quick problem if you make that connection. If you didn't, there are many other tests that will work here. Limit comparison, direct comparison, ratio test, a bunch of them. I think ratio test actually might be inconclusive, so don't do that one. But either way, there are other tests. But I think that was their intent, to connect these two. I think they felt really bad. They're like, we made you do all this work. We're so sorry. Hopefully you realize you can use it. Let's go to part 3, part C. Determine whether this series converges absolutely, conditionally, or diverges. Well, right away, we should probably make sure that this thing doesn't diverge. So to make sure this doesn't diverge, I'm actually going to replace f of n with what it's equal to. So it's the sum from n equals 1 to infinity, negative 1 to the n, divided by e to the n times 1 over n squared plus 9. Cleaning this up a little bit, I think we're going to get the sum from n equals 1 to infinity, negative 1 to the n, over e to the n divided by n squared plus 9. And then think of this as 1 over this fraction. I think it's going to give us the reciprocal of that fraction. So n equals 1 to infinity of negative 1 to the n times the reciprocal, n squared plus 9 divided by e to the n. So that's really what they're asking about. Of course, they made it more complicated this way, but I think this is what they're really asking about here, and we need to think, does this converge or diverge? Well, step 1, is this decreasing? Certainly, because e to the n is more dominant than n squared, so the denominator is going to grow larger than the numerator pretty quickly, so our fraction decreases. In fact, if you took the limit as n approached infinity, this would become 0, nth term test for divergence. And if that happens and we're alternating, this one definitely converges. However, we want to know about absolute versus conditional convergence, and to do that, and I'll switch up colors here, we need to see if the sum from 1 to infinity of the absolute value of this craziness actually converges. N squared plus 9 divided by e to the n. So really, we're looking at the sum from 1 to infinity of n squared plus 9 divided by e to the n. As soon as I see a comparison of two different types of functions, we have a polynomial on top and exponential on the bottom, I usually think ratio test. I think that one sounds pretty darn good to me. It's a great way to compare different things because it takes dominance into play. Really nice way to go. So I am indeed going to do the ratio test here, and I apologize for the lack of space, but I think you'll forgive me one day. Ratio test, so we increase all the n values by 1, like so. And then we divide by the nth term down here. Remember, this is the n plus first term divided by the nth term. I'm going to drop the absolute value because this is all positive as we already took the absolute value. So let's see what happens. We get the limit as n approaches infinity, and I have some cleanup to do here. I'll multiply out the numerator n squared plus 2n plus 1 plus 9 divided by e to the n times e to the first. That was this part right here. And then it's being multiplied by the reciprocal of the other guy, so e to the n divided by n squared plus 9. Nope, n squared, yeah, plus 9. Okay, cool. And again, I'm dropping that absolute value because we know everything's positive. I think a couple things cancel, those e to the n's, right? And then notice e to the first, that's a constant. So to make life a little easier, I'm actually going to factor out 1 over this constant. So we're going to get 1 over e times the limit as n approaches infinity, clean up the numerator, n squared plus 2n plus 10 divided by n squared plus 9. Think dominance, it's n squared, and that all goes to 1. That gives us 1 over e. E again, 2.7, in between 2 and 3. So 1/2, 1/3, somewhere in between 1/2 and 1/3, somewhere in between 0.5 and 0.667. Nope, somewhere in between 0.5 and 0.333. Either way, though, definitely less than 1, which is what we want to happen for the ratio test. Don't forget the ratio test is basically saying we are doing a geometric series, and for a geometric series to converge, the ratio has to be less than 1, and it is. So I've run out of room here, and I imagine you guys have as well. But what is our final answer? Well, we proved that the absolute value of the series converges through the ratio test, so we should state that. And of course, the original series converges through the alternating series test. So if the absolute value converges and the original does, then our series converges, not that, converges absolutely. So thanks for hanging in on here, and hopefully you're feeling decently comfortable on absolute versus conditional convergence. It's nothing too crazy. You do have a little bit of independent practice tonight, but now we are done with our new stuff and we finally get into some review.